Hello everyone, my name is Kadircan Karacan, an electrical and electronics engineering student. Today I am presenting my Physics 102 laboratory project, the experimental verification of Faraday's law of induction using a falling magnet. To fully understand this experiment, we must look at the governing equation. Faraday's law states that the induced electromotive force or voltage is equal to negative n times d phi over dt. Here, n is the number of turns in the coil, and the derivative d phi over dt represents the rate of change of the magnetic flux. The negative sign represents the Lenz's law, indicating that the induced voltage will physically oppose the change in flux. My experimental design links the electromagnetic principle to the classical kinematics. When a magnet is dropped from a height h in freefall, its velocity exactly as it reaches the coil is given by the equation v equals the square root of 2gh. Since the rate of magnetic flux change is directly proportional to the magnet's velocity, substituting the kinematic equation into Faraday's law yields my main hypothesis. The peak induced voltage, Vmax, must be directly proportional to the square root of the drop height. To test this mathematically, I engineered a custom measurement setup. I wound a 200-turn solenoid using an annealed copper wire around an insulating tube. To ensure a highly concentrated magnetic field, I extracted a powerful neodymium magnet from an electronic e-waste hard drive. Then I connected my custom coil directly to an oscilloscope. During the procedure, I released the magnet from specific heights ranging from 5 centimeters up to 30 centimeters. To keep the kinematic equation valid, I ensured the initial velocity was exactly zeroed for every single drop. Because the flux change happens in mere milliseconds, I configured the oscilloscope to single-shot mode, carefully adjusting the trigger level just above the ambient baseline noise to capture and freeze the transient waveform. The resulting data beautifully illustrated the physics. On the screen, I observed a positive peak as the magnet entered the coil, followed by a zero crossing at the center and a negative peak as it exited. Crucially, the waveform was visibly asymmetrical. The negative exit peak was always narrower and deeper than the entry peak. Why? Because gravity continues to accelerate the magnet as it falls through the coil itself. A higher exit velocity means a much larger d phi over dt, resulting in a larger induced voltage. Finally, I extracted the average Vmax values for each trial and plotted them against the square root of the drop height. The data formed a highly accurate straight line. By performing a linear regression, the slope of this line gave me the experimental proportionality constant, and the extremely high R-squared value quantitatively verified the linear relationship between freefall kinematics and electromagnetic induction. Thank you for listening.
Dur. Tamam.
Oo, mükemmel.